In the remaining parts of this chapter, we are going to talk about a really important concept called the flux of a vector field over a surface. Okay? This concept is used all the time in physics. It's very useful and it applies to many situations. Some of them are more difficult to visualize, such as the flux of a magnetic field. That's always a bit tricky. It's difficult to conceptualize in your mind. But it also applies to situations where it is very simple to visualize, such as, for example, the flow of water through a certain area or the flow of air. So in those cases that you can imagine actually something physical that is flowing through a surface, then it's very easy to understand what the flux is. So I'm going to use that situation to explain flux to you, okay? I'm going to always talk about the flux of air through some area. But bear in mind throughout the explanation that this concept of flux actually applies to many other concepts, such as the flux of a magnetic field, which is much less intuitive, okay? So to start with, I thought I could open the flux article in Wikipedia, and this was an interesting experience. So first of all, how does Wikipedia describe the flux? Flux describes any effect that appears to pass or travel, whether it actually moves or not, through a surface or subsistence. A flux is a concept in applied mathematics and vector calculus, which has many applications to physics. Okay, so indeed, here they are saying exactly that any effect that appears to pass or travel through a surface, whether it actually moves or not. For example, the flux of the magnetic field is not anything moving through a surface, but the flux of air is moving, okay? So that's what it refers to. And it has this nice image that hopefully after this video you will understand. More importantly though, I liked this notice that says this article needs attention from an expert in physics. The specific problem is there is confusion between flux and flux density. And I agree, after reading throughout a little bit of the article, that there is a confusion. So hopefully you won't have this confusion when I finish explaining the flux to you. So as I said, I'm going to give you first an intuitive explanation of the flux, okay? So the first thing I'm going to do is assume easy to visualize case. The flux of air. Okay, and then I'm also going to start with another assumption that I will relax later. Assume everything is constant. So we are going to have a constant density of air. So let me draw air molecules. And the density is the same everywhere, okay? These are the air molecules. And these molecules have a velocity. And this velocity is the same for all of the molecules. Okay? So constant density and constant velocity everywhere. And now I ask you, how many molecules of air cross a certain area A? So I draw an area A. And this area A, I'm drawing it such that it is perpendicular to our velocity. So this is now perpendicular, okay? So imagine that my area A is like a net. I'm trying to catch fish with this net, but the fish are the molecules of air. So how many fish do I catch with this net? And not only that, but how many fish per second? Okay, so that is the flux. How many of something per second crosses my net or my area? Okay, so how do you calculate this? Well, the flux is usually written using a symbol, which is symbol phi, capital Phi. And it depends on various things. So let's think about what things the flux will depend on. First of all, it will certainly depend on the density of the air molecules, right? Because if you have twice the density, I draw twice as many molecules in the same volume. So of course the number of molecules crossing my area will also double, right? So the flux is proportional to the density. So I can draw here the density, okay? Now, the number of molecules that cross my area will also be proportional to the speed of the molecules, right? Because if I reduce the speed to twice as much, then of course less amount of molecules will reach my surface, right? So right now with a speed of v, let's say that molecules up to here reach my surface, okay? Molecules that are to the right of that point, they always reach that surface. Molecules that are to the left of that point, they do not reach the surface after 1 second, okay? So remember, I'm always talking about number of molecules per second. So after 1 second, there is like a cutoff plane of molecules that will reach the surface and cross through it, okay? So therefore, of course, if the velocity of the molecules is half, then this threshold will move, because suddenly the threshold will be here. Only the molecules to the right of this threshold will cross my net, but molecules to the left, they are moving so slowly that they will not reach and they will not cross the net after 1 second, okay? So we can add here the speed, v, as a scalar, okay? Finally, what else will make our flux bigger or smaller? Of course, the actual area of the net that we are using to catch the molecules, right? If I reduce my net to half the size, so instead of having the full area, I have only this, then of course the flux, the number of molecules crossing the area per unit time, will be half as much, okay? And therefore the flux is also proportional to the area, okay? So it is proportional to these three things. Let's think about the units of flux, okay? Because now we have an equality for flux. So let's think about the units. So the area has units of distance squared. So let's use meters, which is the most intuitive way, okay? But it could be any unit of distance. Then the speed has units of meter per second. And what about the density? So the density has units of whatever we are calculating the flux of. So this is some quantity. In this case, it's number of molecules per unit volume, okay? So the units are some quantity, so something that we are measuring the flux of, per unit volume, per meter cubed, okay? And therefore we can figure out what the units of the flux is. So the meters, the lengths cancel out, so we get quantity per unit time, quantity per second. So this is exactly the unit for flux. Quantity per second. So the flux through a surface is telling us how much of something is flowing through an area per second. So how much of something per second. If we are counting number of molecules, then this would be number of molecules per second, but we could also count moles. You know that 1 mole is a certain number of molecules. So we could be counting how many moles per second cross our area. And then what will change? So our density, instead of being measured in number of molecules per meter cubed, it will be number of moles per meter cubed. Or maybe we want to calculate the mass flowing through this area per unit time. So this would be kilograms per second. How many kilograms of air are crossing my area? What would change here? The only thing that would change is that this density would not be number of molecules per unit volume, it would be number of kilograms per unit volume, but it's still the density of the air, okay? So my point is that I want to leave this quantity as a free variable. So it's whatever you want to calculate the flux for, okay? Excellent. So this is the flux in this very simple case where everything is constant. Now, one way to justify this equation, which many books use, is to say, okay, after 1 second, which volume of the original molecules, so this is some volume here, so which of these molecules will have crossed my area after 1 second? And the way you can imagine this volume is that this would be like a cube. Okay, it's a cube such that any molecule that is inside the cube, after 1 second, it will cross my area. So the further they are to the right, the further away they get, yeah? If they are just on the edge of the cube, they will just reach my surface and cross it, just cross it. But if we are to the left of the cube, we are outside of the cube, then these molecules won't have time. After 1 second, they won't have reached the surface. So they won't cross, okay? So now this box here contains all the molecules that will cross my surface after 1 second. And this box has a cross-sectional area of A, which is equal to my area, and it has a width which is equal to the velocity or the speed of the molecules, right? Because after 1 second, each molecule will have traversed a space equal to the speed multiplied by the time, so v times 1 second, that will be just v, okay? So if we draw this box with a width of v and a cross-sectional area of A, the number of molecules inside of this box will be exactly v times A is the volume of the box, and then the density is the number of molecules per unit volume. So I multiply that density by the volume of the box, and I get the number of molecules that cross the surface, okay? So this is a technique used a lot in books, imagining this box. Now let's do something else. So here, actually, I want to add an assumption in my list of assumptions. So here, even though I didn't tell you, I assumed that the area is perpendicular to the velocity. I assumed that, okay? What happens if it isn't? Actually, it's very easy. Let's look at this problem from above, okay? So if we look at this problem from above, we still have our molecules. And now our area looks like a line, okay? Because we are looking at it from above. So look from above. So this is our area that looks like a line. And we know that our molecules are moving perpendicular to that area in this case, yeah? So now we can think about this box of which molecules will cross the area after 1 second. And then you can draw this box whose length is the velocity. And this box will tell you the particles that are inside of this box will be exactly the density times the velocity times the area. Now, let's remove this assumption. So what if the area is not perpendicular? So we tilt our net, okay? So what happens then? So I'm going to tilt. So we still have the molecules of air. And to save time, I'm going to copy this twice because I want to draw 2 figures. So I duplicate that here. Okay. So what happens if I tilt my area like this? So it's the same area, it's the same net, I just tilt it. So therefore, I'm going to catch less of the molecules, right? In particular, imagine that I tilt it 90 degrees. So I put the net like this. So now my molecules are moving to the right. And in this exaggerated case, no molecules are going to cross my area per unit time. So here the flux will be 0. Okay. So what about an intermediate case? So here the flux is 0, while here the flux is equal to density times speed times area. So what about an intermediate case? So of course we will be somewhere between 0 and this maximum amount. And actually the way you can figure it out is to still think about this volume. Okay, so now this volume looks something like this. So it has a length in this direction, which is still given by the speed. But now this volume is kind of tilted, right? It's a tilted volume. Okay, so now it's not a cube, now it's a parallelepiped. And what is the volume of a parallelepiped? It's equal to area times perpendicular height or perpendicular distance. In other words, the volume of the parallelepiped is equal to the area A, but now multiplied not by V, but by this distance here, which is perpendicular to the area. Okay, so it's as if we got this box and you tilted it to form the parallelepiped, the volume is still constant. Okay, So we have to account for that projection of V into this direction. And the way we can do that is, you can say that you can define a unit vector, n hat, which is perpendicular to the area. And this unit vector has a certain angle with respect to the speed of the molecules. And let's call this angle alpha. Okay. So therefore, this angle alpha is the same angle that appears here. So then the volume of this parallelepiped will be A times V times the cosine of alpha. Okay. And therefore the flux in this case will be equal to the density times the volume of the parallelepiped, which is V times A times cosine of alpha. Okay. And now this makes sense that here alpha is 90 degrees because our normal vector is pointing up. So the cosine, so alpha is this angle here, which is 90 degrees. So cosine of 90 is 0. So we get 0 flux. When the angle is 0 degrees, we get the original flux. And for any intermediate angle, we get this expression that includes the cosine. Okay, so this would be our equation for the flux, even if the area is not perpendicular. So now we are accounting for that angle. Now there is a nice way to write this. Instead of using the cosine, is to use a dot product. Okay, and the way to do it is, if we know that phi equals density times the speed times the area times the cosine of the angle, we can write this as the density times the velocity vector dot product with the area vector. Now wait a second, what do I mean by the area vector? So the area vector has a magnitude or a length equal to the area and has a direction n hat perpendicular to the area. Sorry that I was blocking the text there, perpendicular to the area. Okay, so this defines the area vector. So whenever you define an area which has a certain cross-sectional area, scalar A, you can define the area vector as a vector that is perpendicular and is pointing in the direction, perpendicular to the area, and the length is given by the area. And this defines an area vector. So now by doing the dot product between the velocity vector and the area vector, this includes the cosine of alpha, okay? Because remember that alpha was the angle between the velocity and the normal to the area. So we can use this trick to write the flux, okay? And now we are going to do one more simplification. So we are going to group, let me move this slightly to the left. So we are going to group these two things, the density times the velocity of the particles. We are going to group it, and we are going to call this vector, we are going to give it a name, and the name of this vector is the flux density. Okay? Think about the units of flux density. So flux density in books is usually given the symbol J, either capital J or small j, it depends. I have seen both. So J is equal to the density of whatever quantity per unit volume we have on space, and in the direction and with the magnitude also multiplied by V. Okay? So what are the units of J? So if this is measured in quantity per unit volume, and then this is a vector which is measured in meters per second. So this flux density is measured in units of whatever quantity per unit area per unit time. Okay? So this is a vector that is defined at every point in space, which tells you how much of something is flowing. So this flux density is telling you how much of something is flowing per unit area per unit time at this point. Okay? So it's just the density times the velocity of the things that are flowing. So the density of things that are flowing and the velocity of the things that are flowing. Okay? Flux density is often used for any quantity that is conserved in physics. So for example, any conserved quantity in physics. for example, the mass, you can define the mass flux density and that would be J, maybe J mass, and this would be measured in kilogram per unit area per second. Okay, so how many kilograms are flowing at this point per unit area per second? Okay, it's also common to do it, for example, for the electric charge, and this would be the charge flux density, which is often called JE, which would be coulomb per meter squared per second. But this is often given another name because, as you know, coulomb per second is also amps, is the current, right? How many, the charge per unit time. So this is also measured as current per meter squared. And this is often, even more often than charge flux density, we call it the current density. So this is used a lot in electromagnetism, okay? And in fact, any other conserved quantity, I mean energy, you can also calculate the energy flux density. Okay? And the key thing about this flux density is that if the flux density is constant, in space, then the flux through a surface is equal to the dot product between the flux density and the area. Okay, that's exactly the equation we found here. We just grouped these two together as flux density. So the total flux through an area is just flux density dot product with the area. Okay, so let's do a picture here to remind ourselves of this. So we have some area vector, which is in the direction normal to the area. And then we have some constant flux density, which is at another angle. I don't know what angle this might be, but it's an angle that crosses the area. This is the flux density vector, J. So the flux through this surface will be equal to the dot product between the flux density and the area. Okay? And this is true if the flux density is constant in space. So now finally we are ready to consider a case. So we already said that the area is not perpendicular. So now let's drop this assumption that everything is constant. What if everything is not constant? What if things are changing? Okay? So what if things are not constant? For example, what if I have the density of air is higher here and it's getting less as we move up? Okay. And also the velocity of air, maybe it's higher, maybe the velocity of air is higher here, but it's getting slower as we move down. Something like that. Okay, so something that changes. So this could be defined by a flux density J that depends on position. Okay, so different positions have a different flux density J. And remember that this J is accounting for both the density and for the velocity. It's actually the product of both. Yeah, J is the density times the velocity. So this J accounts for the two effects. Okay, so you have a certain J that depends on position. Okay, so now you want to calculate the flux over a certain surface. And maybe this surface is no longer a rectangle. Maybe now I want to do a weird curved shape. Something like this. So my net is now some curved surface, S, which we parameterize using R of UV. So a parameterized surface. So now what is the flux here? How are we going to calculate this flux? And the key, as always, is to do an integral. Whenever things vary, we solve it by doing an integral, right? Let me give you an analogy. If you know that the speed of a car is constant, the velocity of a car is constant for a certain time, you can calculate the total distance traveled by the car by doing velocity times the change in time. and that's a simple multiplication. Yeah. But what if the velocity of the car is changing with time? What do you do then to calculate the total distance covered? Well, you do an integral. Right? That's what you do. So that's why integrals are useful, because integrals are saying, I'm dividing the path of the car into tiny intervals. Yeah, so maybe the car is going slower here, then it goes faster. But for each of these differential intervals, I know that the dr, the distance covered in this tiny interval, is going to be the instantaneous velocity at that instant. So you know that dr will be the velocity times dt. And this is exactly what you are putting inside of the integral. So you are adding up all of those drs by doing the integral between time equals 0 and time equals t. So you know that the integral always solves the problem when things are not constant by dividing the problem into tiny bits and assuming that on each tiny bit the thing is constant. So the velocity is constant when you are only considering an interval dt, because it's an infinitesimal interval. So that's exactly what we are going to do. So we divide surface into tiny ds's, yeah. So our surface is now divided into tiny ds's. So for example, let's consider one of those. So this is a differential ds now. But this ds, contrary to what you have been learning, now this ds has a direction. It's a vector ds. And now we have the flow, the flux, which was changing. But it doesn't matter because at this point you have a certain flux. So this is the flux density as a function of position. So now the differential flux going through this differential surface will be equal to the flux density at that point multiplied by, or dot product by, ds vector. Okay? Maybe let me write that bigger because this is very important. Which means that the total flux is going to be given by the surface integral of these differential fluxes, which is going to be given by the surface integral of the flux density dot product ds vector. Okay, so that is going to be the total flux for any surface. Okay, and this is what I'm trying to show in this figure from a textbook. So we have our flux density, which in this textbook is identified by letter F vector. And then we have our delta S, which is our ds, which has a direction given by n hat, which is normal to the surface at each point. Okay? So this is the equation to calculate the flux of some quantity over a surface. And it tells us how much of that quantity is flowing per unit time. Okay? Through that surface. So that was a very long video. I mean, this was your first explanation of flux, so I covered lots of concepts here. I hope this is clear, but next we are going to see how to actually define this integral and how to calculate it. Okay? So see you in the next video.